Thank you, AB, and thank you, Andy, for having us today. My talk is about using machine learning methods to predict high-latitude ionospheric convection patterns. And if you are wondering what these are, here's a photo taken by Ashton Reimer showing a Canadian SuperDARN radar. So you can see the radar here and the aurora on the night sky. And you can see that the aurora has some interesting patterns. So when we talk about plasma convection, we talk about these like kind of the vectors that I drew on top of this image. And these radars you see here are operating with high frequency signals to detect these plasmas overhead. So this is the kind of the high latitude ionospheric convection pattern we are interested in. And I have to find how to propagate my slides. Perfect. So this plasma convection is very important for the electrodynamic coupling of the Earth's magnetosphere and ionosphere systems. This is basically how the whole plasma is convected in the magnetosphere, and towards the magnetic fields, the foot points on the ionosphere creates this ionospheric convection patterns. This is predominantly driven by the solar wind and magnetosphere coupling, and the interesting part is during intervals of weak electromagnetic forcing, we see that Earth's upper atmosphere, the neutrals, start to interact with the ions and starts driving this plasma process. At high latitudes, we can use this ion convection velocities to infer what the electric field is. That's why it's very important for the electrodynamic coupling. This is basically how the energy and momentum is transferred. This is, of course, a very large-scale picture that we are looking at, and a multi-scale understanding of this ionospheric electrodynamics, and by association, this convection is still not achieved. The first radar that you have seen in the title slide is part of the super dual Auroral radar network, and this network is basically how we understand the ionospheric convection patterns in the northern and southern hemispheres. This is a global network. It continues to operate at the high frequencies, and each individual radar span mid to polar latitudes. So you can see this image created by Evan Thomas, and this shows basically the locations of each radar and their fields of view, and whether these fields of view are attributed to mid, high, or polar regions. You can see that the coverage in the southern hemisphere here on this plot as well. And this is basically what makes SuperDARN a very powerful tool in understanding space weather at different scales, and also globally, because this type of coverage is unprecedented comparing other ways of measuring the space weather phenomena. So there are a lot of ongoing efforts to model the ionospheric convection. Is because of its importance. One product is derived through the SuperDARN radars, and through the SuperDARN group, it's regularly updated and provided for the community. These ionospheric potentials are parameterized by the interplanetary magnetic field clock angle, solar wind electric field, dipole tilt angle, and the planetary geomagnetic disturbance indices. In addition, we have other empirical models like the Weimar model, which depends on the Dynamics Explorer ion drift meter measurements, or more assimilative models like the AMI model, which uses the ground magnetometer perturbations to infer these overhead electric potential patterns. There's also a recent random forest model by Bill Bristow using SuperDARN grid data. But you can see both all these models can produce wildly different results. Here we are looking at the Weimar model at the SuperDARN potentials taken at the same time, which is the 2nd March 2017, 14 past 7 UT. You can see that the Weimar model shows these two-cell convection pattern of ionospheric plasmas, and it has, in general, larger values. Whereas the SuperDARN potentials here they are more structured, but they are weaker and more confined into the region over 60 degrees. So you can see that these models differ significantly, and the main reason is because they are trying to resolve different scales. Weimar model is a more quasi-dynamic model, which means that it is trying to resolve larger scales, while the SuperDARN potentials and fitting tries to again find an overall picture, but with more measurement-based input. So the motivation for a meso-scale model comes from understanding how the SuperDARN data is gridded and turned into the SuperDARN potentials that we have just seen. First of all, these radars all are operating in identical modes, which means that the radars that we have seen before are creating a 2-minute resolution data, which is really temporally small enough for us to be able to find more dynamic structures. So the potentials that the SuperDARN group regularly provides have a resolution of 10 minutes. But if we are to look at the radar and their observation, there is a data that we can really utilize that has this 2-minute resolution. In addition, these radars are measuring the line of sight velocities, which can be converted to the latitudinal and longitudinal velocities, which means that for specific radars, we do not really need to parameterize the output. We can really go and take that velocity information and try to build a model based on that. In addition, there are overlapping regions with the field of view, as you can see. And based on the radar geometry, some measurements are more reliable than others. So instead of, again, looking at the grid and these interpolated velocities, we can really look at radars which are operating in more reliable modes or in certain magnetic local times that can have the geometry to resolve certain structures better. So this is something that also can be utilized to build the meso-scale model for the convection. And again, if we try to come up with this machine learning based predictive model, we no longer have to bin the IMF and the solar wind parameters. So we can really look at the variation between the certain drivers as well. So it will help us better specify what the output potentials could be. And then lastly, if there are not good enough data, SuperDARN potentials omit these intervals. So with a machine learning model or a predictive model, we can really fill in those gaps. Here you can see that also with the SuperDARN model, because these products are provided as a potential, there is the Hepler-Maynard boundary condition that is applied around 60 degrees. So even if the radars could have velocity measurements below this boundary, they are discarded because of the fitting that is applied. So there are all sorts of valuable information if we revert back to the original SuperDARN data and try to use it for the predictive model. That is why we built the data set based on the SuperDARN Prince George radar gridded data. We started with around 6.5 years between starting from 2010 to 2016. And we converted the line of sight velocities to latitudinal and longitudinal velocities. We have also employed the magnetic latitude, the magnetic local time, day of year type of parameters to understand the variabilities that might stem from the ionospheric conductivity. We have included a 30-minute time history for the system in the solar wind and interplanetary magnetic field parameters. We have also included geomagnetic indices because these parameters are mostly continuous. We went back to the 2-minute resolution, that's the higher resolution that we can utilize for our predictive model. And this results in around 40 million data points and more than 160 variables. We tried various different models, but we settled on the multi-layer perceptron model, and all our parameters that you see, like the separation of the training, validation, and test set versus all the parameters that you see here, have been studied within the given range using the AX client and Keras tuner packages on Python, and we have come up with the best selection, as you can see, and multi-layer perceptron model structures here that you can see with 2 hidden layers and certain batch normalization and dropouts applied after each layer. So let's see how the model results look like at a glance. I don't know if you have seen this bow tie type of distribution, but this kind of the distribution we tend to get when we are trying to predict something with a polarity, meaning that that has that directionality. So here we have the longitudinal velocities, and here we have the latitudinal velocities. On the y-axis, you see the test values from our test set that we preserved, as you all know. And on the x-axis, we have our model predictions. And here you can see our overall correlation is 0.85 for longitudinal and 0.86 for the latitudinal velocities. Again, the empty quadrants means that the model does not predict a wrong directionality when for these test cases. And overall, what we see is that in general, a model that can predict the general behavior of the system. Looking at this results for Prince George radar in a bit closer detail, just as a reminder, the Prince George radar is located here, sampling the high latitudes. You can see it's located in the around 60-degree magnetic latitude and minus 64 degree in magnetic longitude, scanning in the west direction. Here you can again see from our test set comparison selected for a certain latitude, we can see that the model performs compared with the data well. There are certain times that it can overestimate or underestimate as usual, but overall we can see that most of the variability now is captured. And you can see this is in spanning through certain months. There are significant data gaps which this model could be very useful for. So this is not like a always measurement recording radar, right? So it's not always registering or measuring things in a uniform grid. That's why it's really helpful to see it in a temporal time versus velocity comparison as well. So each of these vertical lines here has almost like a few hours span. So we cannot see them in this view, but we can look, for example, a day and see how the radar measurements perform with our predictions. And you can see in the red is our, again, model predictions, and the black vectors show the SuperDARN convection patterns. Again, overall, you can see that the directionality is well captured, which means that when we have the latitudinal and longitudinal directionalities predicted correctly in various different times. So to make more use of this information, we also looked at the BIND 2D profiles for the longitudinal and latitudinal velocities, correlation coefficients, and the mean absolute errors as well. Here are the Pearson correlation coefficient results. So when it's really dark blue, it means that we have a really good agreement between the test data set and our predictions. And so here, for example, for the longitudinal velocities, you can immediately see around the dome region between 70 to 80 degree magnetic latitude, we have a really good correlation. This is a region that our model performs the best. And for the latitudinal velocities, we have some sort of a piecewise type of performance evaluation. Here you can see between 70 to 80 degree down to pre-noon region does really well and correlation. And then here as well, between 65 to 70 degree post-noon to the afternoon sectors also record high correlation coefficients. In the mean absolute error sense, what we see is on the longitudinal velocities, the post-noon sector between 60 to 70 degree records a high mean absolute error. So it is lowest here in the midnight to daytime, basically below 65 degrees. And the mean absolute errors in the latitudinal values, they are really high at very high latitudes, but lower, for example, between dusk to 22 MLT, around the 72 to 80 degrees, and in these lower latitudes. So this is basically constitutes the main principle of how we want to merge these radars. For this Prince George radar, we know where our radar does better because of it. We include its radar geometry as well. So let's see how other radars perform. For an example, I'm going to show you the King Salmon radar results. Again, we can see that both high distribution again in different quadrants. This time we see a little, we use a very similar model setup for this King Salmon radar as well, but this one has from the beams you can see almost 20 times less data points than the Prince George radar. I'll go to the next slide so you can see where the King Salmon radar is. You can see the PGR was here and King Salmon radar is here. So based on the differences, you can see that they are separated in the magnetic longitude by around 2 hours magnetic local time. And the King Salmon radar is also around 2 degrees lower in latitude. And the way, like the field of views sample at times have like an overlap, but at times differ as well. So this becomes valuable information when we are trying to predict and reconstruct the convection pattern. Here, when we look at the times, you can see again there are certain time intervals where the over predictions happen and under predictions happen. But overall, again, we see a vector profile that is a little bit more complicated because this time the polar convection is also noted in the King Salmon radar. But overall, again, we see the main convection being captured very well. Again, looking at the Pearson correlation coefficients and mean absolute error, now we see a little bit of a different picture, especially with the mean absolute errors. But let's start with the correlation coefficients. Longitudinal wise, the highest performance goes to 75 to 81 degrees from down to pre-null sector in longitudinal velocity. And in latitudinal velocity, we see in a similar region a little bit higher latitudes, spread a little bit wider, this region where the model performs better. By means of mean absolute error, these are definitely larger than the Prince George radar, especially with the spread towards the post-noon to pre-midnight sectors here. And you can see a similar behavior in the latitudinal velocities, a little bit clustered around the noon sector as well. So basically, this means that the King Salmon radar does not perform as well as Prince George radar overall, but there are regions that it records and overperforms compared to Prince George radar. So again, these like variability would be very helpful while we are progressing towards building a multi-scale predictive model. So what are the immediate next steps for that is to complete this region model by in a congregated manner using the other high latitude radars, and then also explore the radar performance with respect to different scan directions. So the way that the data is collected is immediately relevant with how our models are performing because of the radar geometry and the scanning directions. In addition, because this is we are trying to build this multi-scale predictive model, it is important to evaluate the performance of physics-based scenarios. For example, whether the model could capture IMAP-Z reversals, the changes in IMAP clock angle, for example, the sharp changes in BY, or whether it can record like a strengthening of the plasma convection velocities due to compressions of the magnetosphere. So in the long term, our deliverable is to, we are hoping to deliver an operational multi-scale ionospheric convection model for both northern and southern hemispheres. And these kind of convection models can be used for driving the general circulation models with multi-scale energy and ionospheric specifications. These SuperDARN results can also be used in assimilating models like the AMI, AMGEO, or HIME type models, which incorporates these radar information to the large-scale potentials. So that is all that I have. Thank you.